Okay, so let's get underway again. So this slide, I just find it amusing. It was an image that was sent to me by one of my students 3 or 4 years ago now. She just graduated this last year. Uh, but um, I've given it the name Data Analytics in Legoland, but it is much of what you did previously of organizing data, trying to make some sense out of it, finding some patterns in it, looking at graphs about it, then building a model, which was part of building a story. And that's where we'll end this course, is how to do the storytelling. Anyway, let me just change my headset here. Yep, I can't find it. Anyway, let's get going. So again, I'm still in Halifax. Dora is still in Kingsburg. This is from when we were down there on the break. And why Kingsburg? It's my wife's, it's where my wife grew up. And all of her family is originally from that sort of area. And if we go back to the 17 and 1800s, her ancestors are buried in this area. And this is the cemetery in Kingsburg. Um, they have a sign called Der Strandhof, Strandfriedhof. My German is not as great as it should be. Um, it's the beach cemetery. Strand means beach in German. And this is the headstone of one of her ancestors that died in the 1800s. Anyway, on with the show. So we've got a test coming up on Friday. I hope you do well on it. Assignment 4, I posted it. I think I did. And I'll do a tutorial next week on how to help you with that. Discussion 9, which is due next week, not this week. It's a challenging issue in stats when you take it. And they get into decision making using data and with trying to prove things. Can you prove a claim? And the trouble is, of course, that you're not always right. This is really a classification problem. And a certain percentage of the time, you're wrong. And the classical way of doing decision making in statistics is to specify up front how big a risk you're willing to take of making a wrong decision. Can you actually do that? Can you, in advance, if you were told to gamble on something, could you specify in advance how big a risk you would take of losing on this gamble? And could you really put a number on it? It's actually a really hard thing to do, but that you have to be able to do statistical decision making. Anyway, and of course, we've got a quiz coming up. So what's coming up on Wednesday? It's the famous Ides of March. If you had to do Julius Caesar in high school, Shakespeare play, Beware the Ides of March, still sticks in my head anyway. That other things, I thought we already had this, but it's National Peanut Lovers Day. Peanut butter. Well, peanut lovers. I love peanut butter as much as I like peanuts. Maybe it was Peanut Butter Day that we celebrated. And World Contact Day, about contacting aliens. I don't know. Ever think about that? Anyway, something across. Anyway, let's get going. So last day, we introduced a whole bunch of different bits of jargon associated with probability, that we define something as an event that's going to occur or not occur. And it's generally something that happens in the future. The chance someone is going to default on their loan, or they're going to buy this product or click on my advertisement. It focuses on the future or something that's hypothetical. If it's already happened, probability doesn't apply. Although an awful lot of people seem to act like it doesn't. If it's already happened, you're right or you're wrong. We get a variety of different types of words associated with having two events, like both of them happening together. That's and. Or one happening, or the other happening, or both of them happening. That's or. We sometimes look at complements. An event happens or it doesn't happen, one or the other. We get a formula out of that. You buy something or you don't buy it. That we get an addition rule that we've got. What's the chance of A happening or B happening or both? And it's not the probability of A plus the probability of B plus the probability of both. It's actually A and B minus the probability of both, because the case of both is included both in A and in B, and we have to avoid double counting. So we actually have to take something out. There's a special case called mutually exclusive, when if A happens and B can't, or if B happens and A can't, one or the other must happen, but you can't have both of them, or neither one happens. In that case, that last term of both happening drops out, and you get a simpler rule. We'll sort of see that later on. A conditional probability is the most important topic that we cover in probability, one of the most important topics in data analysis, that we are frequently looking at what's the chance of something happening, and we've got a lot of information. We've been building models to do that. A classification model, like predict, is it, are you an A or a B? And we've given information on who you are. That's a conditional probability. A special case of that one is called independence, where knowing some piece of information is irrelevant. Trying to predict what the weather is tomorrow, given what your hair color is, or when you were born. Of course, they're independent. I'd hope so. But sometimes we find some variables that we think are important in making decisions, when in fact they're not. That if that variable happens or doesn't affect what our outcome is. That's important to know. So we'd like to know what are important variables and what are unimportant variables. Unimportant ones are ones that are independent of the outcome we're studying. It also simplifies our multiplication rule that looks sort of messy, that you see at the bottom of the screen here. If the chance of A and B happening, I can just multiply probabilities together. It makes it really simple. We're going to see that next week as a way of simplifying how we do classification. So the rule for doing this, and we'll use this in a few minutes, is the probability of A and B is probability of A given B times probability of B. Or if you were given A, then you would multiply by the probability of A. So it's important to get the sequence right. When they're independent, it means those two variables are not correlated in any fashion. There's no relationship between them. Sort of like what we had in value estimation. So why we care about this is that classification involves predicting a category, and many of those models don't predict the category, but they predict a probability, and then we make a decision. So we need to understand that probability, and those probabilities are conditional. We're estimating a probability conditional on information we have about the customer. So it's important to have a good understanding of that conditional probability stuff. Now, as I said at the end of last class, maybe you understand all this. It seems quite simple, but let's put it into practice, and particularly about conditional probabilities. So with big problems, how do you break them down? And large problems are hard. Any type of problem, big problem, is hard to tackle when you've got so many things to think about. So we like to break it down into smaller pieces that we can get our head around, and then link the pieces together. Sometimes that can be really messy. Sometimes we can see the different pieces as being in a sequence. I'll do this first, then this, then this, then this, and do it in a sequence. And we sometimes get that with probabilities. So often when we're breaking things down, we use a chart to link the pieces together. I call them a goes into chart. What goes into what? A special type is one that we just call a tree, where things all just move forward. We never go backwards. And these charts, we use them for an awful lot of things. Anytime we're breaking something down into smaller pieces, we need this linking mechanism in a chart. And we do that with a very, very large number of problems. If you take a course in operations management, they will talk about that type of issue. So here's an example. And this one I left you with at the end of last class. And it was done as an experiment. And we'll do it similarly, a similar example in a minute that is quite different. Well, it's the same, but different. So the experiment was to try to understand whether or not people have a good appreciation of probability. And the experiment was set up by getting this group of doctors to try to predict whether or not a patient had cancer or not. And they were told information about the patient and information about diagnostic tests that were given to the patient. So the patient is a woman that's 40 to 50 years old, and we're trying to predict whether or not this woman has breast cancer. For this group of individuals, we're told that about 1 in 125 develops breast cancer. And the diagnostic tests we're going to use on this person, like a classification model, is a mammogram, very widely used procedure for testing for breast cancer. And we're told that if you have cancer, 9 out of 10 cases, the test comes back saying, being positive, suggesting, hey, you've got cancer. Unfortunately, it also makes mistakes. It already missed 10% of the ones that had cancer, but it makes another type of mistake. Among those that don't have cancer, in 7 out of 100 cases, 7%, it comes back with a positive test result, even though the person didn't have cancer. But you've got someone really, really scared right now with a positive test. So anyway, this is a test procedure that is right most of the time. If you have cancer, 90% of the time, it says you have cancer. If you don't have cancer, 93% of the time, it says, I don't think you have cancer. So it's quite good in that regard. So the doctors were asked to pick, well, how often do you think? Or what do you think the chance is of this woman that has a positive mammogram? What do you think the chance is that she has cancer? And they were given several choices, and almost all of them picked 75%, because this test works almost all the time, makes very few mistakes. Do you think that's an accurate assessment? So we can look at this. Let's start out. We've got women have cancer or they don't have cancer. That's the first piece of information we're given. 8% or 0.8% do, 99.2% don't. So this is like our complement rule. Either you do or you don't. So in a tree, we'll look at these two branches and then see what happens with them. Then we get our test results. It could be a positive test or a negative test result. Depends upon whether or not you have cancer. Positive test is 90%, negative test result 10% if you have cancer. If you don't have cancer, the numbers are different. We can then use our multiplication rule to go and look at the ends of the branches. What's the probability someone gets a positive test and has cancer, or gets a negative result and does not have cancer? I combine the two events. So I throw them all together with all this multiplication formulas. You may have no sense of where all the numbers came from at the end here. Don't worry about it. Let's go back and try it a different way. Not my idea. this was taught to me by some students that were not my best students, but they were very pragmatic. And I must say they had a very good handle on how to address these problems in a fashion that they could interpret as opposed to this technical formula approach that I had taught them. And this is how they did it. And I recommend this is how you might want to try doing it. It's how I do it now. They said, let's start out with 100,000 women. Start it with a very large group. 0.8%, 1 in 125 has cancer. How many is that? Turns out it's 800 women. So 99,200 don't have cancer out of this group of 100,000. Okay? So they're making it a concrete problem. And then they ask, well, what happens when we give a mammogram? Well, positive test happens 90% of the time with those with cancer. How many women is that? Negative test happens 10% of the time. How many women is that? So they split it up. That, well, 90% of 800 is 720. 10% of 800 is 80. I still have 800 women. Okay. And of the 99,200, 7% test positive. Pull out your calculator. You're going to need it for this. 7% of 99,200 is 6,944. And 93% is 82,256. You might have a sense why they picked, why should we be looking at 100,000 women? They picked a big number so that they wouldn't have to look at decimals, that they'd get answers that were whole people. We've used our formulas here in doing this. We've used our multiplication rule, whether you've seen it or not, but they just reasoned it out using common sense. I hope you followed that. So then they took this stuff that traditionally we would have put it into a probability table. I'm going to just jump over that. I'm going to put it in a frequency table because that's what these guys did. They looked at the 800 women that had cancer, the 99,200 that didn't, split them up into the positive, negative mammogram results, summarized it all in a table. So we've still got all 100,000, the ones with cancer, the ones without cancer. That the 800 that they started with cancer, they've still got 800. 720 plus 80. The 99,200 without cancer, they've still got 99,200. They put it into the table in part to check their arithmetic to make sure that their row totals added up to what they thought they should be. Once they'd done that, they felt good that they'd done their work correctly, and they looked at the column totals. How many positive test results did we get? How many negative test results did we get? Added those up. All right. What do you do with this? Well, if you have a positive mammogram, and this was what the doctors were asked, what's the chance you have cancer? So how many got a positive mammogram result? Well, I can show all the probabilities and the decimals. Let's go jump to what they did. They said, well, 7,664 positive tests happened, but only 720 of them had cancer. And so about 9% of those with a positive test really had cancer. Not 75%, 9%. Ooh, what happened? Okay, this is very strange. So really, we're looking for something that's quite rare, 1 in 125, 0.8%. I can't picture 0.8%. It's a tiny number. That our test is right most of the time, but actually the chance it makes a mistake is much higher than 0.8%. It misses those with cancer 10% of the time. It misdiagnoses those without cancer 7% of the time. So it makes a lot of mistakes relative to how frequently the cancer actually occurs. So, should we bother using this? It makes so many mistakes. Um, it has been good in one respect. It's our first stage in doing testing. It doesn't make the decisions for us. Before, our guess would be 1 in 125 have cancer. Now we've got 1 in 11, 9% of those that got a positive test have cancer. So we've gotten down to a smaller group. I've got better than I was before. That I filtered it down. And now maybe I should apply a second test, like a needle biopsy, and look at a tissue sample to determine whether or not this person has cancer. It's sort of like we did with value estimation, putting in one variable by itself. Yeah, it was useful, but it gave bad predictions. So add in a second variable, a third variable, a fourth variable. We'll do the same with classification. Add more variables in to make better predictions. One variable isn't enough. One test isn't enough. But it still seems counterintuitive. The probability of a positive test if you have cancer is 90%. But the probability you have cancer given you have a positive test is 9%. Flipping things around, A given B versus B given A, give me completely different answers. It's really easy to make that mistake. And that's why a lot of people have trouble with probabilities. That this process we went through, flipping things around, of going from one to the other, cancer given positive, when we've got probability of positive getting cancer, you can express that, the whole thing, the whole steps we went through as a formula. It looks pretty ugly, doesn't it? If I used A's and B's, it's still pretty ugly. It's known as Bayes' rule. And Bayesian analysis is a very important branch of statistics. It's a very common strategy in machine learning and artificial intelligence. So if you come across this term Bayes or Bayes analysis, this is where it's coming from. It's flipping things around. It can get quite complicated, but as we just saw with the trees, maybe we can use tools so that we don't have to think in terms of messy formulas. So let me give you another example. And this one, well, it's now hopefully fading into our distant memories, is doing rapid tests for COVID. Still doing them. I've still been doing them. When they first came out, we thought they were a really big game changer. So I remember reading an article. It was in the summer of 2020. So we're right in the middle of the pandemic. Everybody was, our lives have been ruined by this. We can't do anything because we don't know who has COVID. And it's too complicated to go in and get these PCR tests done. And they don't tell you until a week later. It was awful. And Abbott Laboratories, a big pharmaceutical company, came out with a rapid test. And it got approved by the FDA in the US. And that it only costs $5 to do the test, cheaper now. But it looked for antibodies and to try to identify whether or not you might have COVID. It's very different from a PCR test. And it took that nasal swab, and it was sort of like those quick pregnancy tests. And you've probably done a rapid test. When I was first talking about them, we hadn't seen these things. And the initial reports were that it was really, really good. So they said, and this was their word, correct positives 97% of the time, correct negatives 98.5%. What they meant was if you had COVID, it gave a positive test result 97% of the time. And if you didn't have COVID, it gave a negative test result 98.5% of the time. So almost all the time it was making the correct diagnosis. So the thought was, this is going to be a game changer. We can fly again. We'll know if the people on our plane have COVID or not. So what we didn't know was how many people had COVID. Like, how do you find that out? You aren't going to go and test the whole population to find out. We couldn't do that. So it was playing a what if game. So what if 1% of your population, 1 in 100, had COVID? What would happen? And in Nova Scotia, that's what we thought we were at, that most people didn't have COVID. We were one of the last places to get really hit by the virus. And that, so I can go through all the math. This looks really confusing. So let me jump to what my students did. Let's take 100,000 people getting a rapid test. 1% or 1,000 of them have COVID. 99% don't. That of those that have COVID, that 1,000, I can identify 97% of them. That was 971. I missed 29 cases, but I got most of them. And of those that didn't have COVID, at 99,000, 98.5%, I'm going to give a negative test result. Unfortunately, that only adds up to 97,515. So 1,485, I'm going to get a positive test, but they don't have COVID. Here it is in my tree. So starting it with 100,000, 1% go up one branch, 99% go down the other. That's our complement rule. Got to go one way or the other. And then, so I'm drilling down to 1,000 with COVID, 99,000 without. Then I've got my test. So 97.1% give a positive test. So 2.9% have to give a negative test. My complement rule again. And similarly here with the negative and positive, if you don't have COVID, I extrapolate it out, I get all my results, and I can take this, build a table, summarize what my test results are. So about 1 in 40 are coming up with a positive test result. That's the 2,456 tested positive. And among those, how many had COVID? 971. That's about 40% of them actually had COVID. So 60% of the positive test results didn't have COVID. Now, among those that tested negative, initially it was 1% didn't have COVID. Now it's down to 3 in 1,000, 0.3% have COVID among those that test negative. So of those, if you tested negative to get on the plane, a very, very small percentage might have COVID, okay? Which sounds good. It means it might be safe to fly. On the other hand, that we've got a very large number of people that were told you can't get on the plane because you got a positive test. You can't go to Cuba with the rest of your family for March break because you got a positive test. So either the family goes and you stay home or you cancel your trip. What are you going to do? You can imagine how many upset people there would be if that was the way we dealt with this. Because the thought was initially that when you checked in for your flight, you'd get a COVID test. By the time you got to the security check to go through and have your, they do all the scanning and all that type of thing, they would already have your test results and they could stop you right there. So you'd never even get to the boarding area. Well, this didn't look really good, did it? If it was only 1 in 10,000, not 1 in 1,000 that had COVID, what happens? Well, almost every test result will come back as a false positive. That of 155 positive tests, 154 would not have COVID. Only 1 in 155 would. It screens out really, really well those that don't have COVID that, or if you got a negative test, the chance you've actually got COVID is super, super small. So it's really safe to fly. But that's done at the expense of a large number of customers that are being told they can't get on the plane because they got a positive test result. We're going to look at this next, well, 2 weeks from now, when we look at the types of mistakes that we make with our classification test. That last winter, a year ago, during the peak of Omicron here, it was about 3 in 10 in Nova Scotia was infected. And well, that's their best guess anyway. And that if you got a negative test, the chance you had COVID was about 1 in 80. So it went from 3 in 10 to 1 in 80. So that's pretty good. That if you had a positive test, it's almost guaranteed you had COVID. It was working really, really well. So rapid tests in Nova Scotia were widely advocated last winter because there was widespread outbreak of the disease, and the rapid test was a really good preventative measure. So it works well if it's common. Unfortunately, it didn't work well if it's uncommon. How do you know? It's hard to deal with. So these trees that we've got are a simple way of trying to explore this type of thing. We didn't get into fancy math to be able to do it. And we can have more than 2 branches. You could have, when doing a test, doing a classification, you could have multiple outcomes. Yes, no, maybe. And then after that, you could also go and branch further. That if you get a positive test, like with a rapid test, if you got a positive one, you were encouraged to go on and get a PCR test, which is more accurate than the rapid test. Not perfect, but it's more accurate. And you could have successive tests. So it's like using multiple variables to make your prediction. You'll make better final conclusions by doing it. So we can keep branching a long way, and we can have many branches. That if you were in sports, like the Olympics, they test for banned substances. They don't use just one urine test. They will use multiple tests, and they may use both urine and blood tests, and they'll do 2, 3, 4 tests before you're disqualified. So multiple screening is standard practice. That if we were doing this to screen customers as to whether or not they would be good or bad, are they good borrowers? Should we give them a loan? Are they bad borrowers, and should we not give them a loan? If your test is imperfect, you may be disqualifying a lot of good borrowers. So you need to have a good sense of what this sort of thing is, because the classification model may appear to be doing well, but when you put it into practice, you may see different results from customers coming back. Okay, that we got to think about, and we'll think about that more when we get into how to evaluate classification models. It's a lot more complicated than it might first appear. Okay, so next day we're going to look at 2 methods for classification. One of them uses this tree idea of split, 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 and it's very, very similar to the tree, but it's used differently. The other one looks at that Bayes rule and says, too complicated. And that was just for A and B. If I had A and B and C and D, I had many, many different variables I was using to predict an outcome. I bet the formula would be just ugly as can be, and it is. So can I simplify that in some fashion? And when simplifying, is it still going to give me valid results? Turns out it does. But we'll get to that when we look at the case next class. And we're done. Thank you.